Good morning, students. In the last session, we have discussed about the different type of the approaches which are used for the synthesis of nanomaterials. That is by top-down approach and bottom-up approach. So in top-down approach, the bulk material which is converted into the nanoparticles. In bottom-up approach, the atoms, molecules which are converted to the by the self-assembly, by the joining of layer by layer, or by the formation of the bonds, we get the nanoparticles. That is the bottom-up approach. In the last session, we have discussed about the ball milling process. So high energy ball milling process, in which by the attrition process, the material or the nanomaterials are being synthesized. In the last session, we have discussed about the lithography, that is used to prepare homogeneous one-dimensional or three-dimensional nanomaterials. That is this material which is having advantage of both top-down approach and bottom-up approach. The preparation of the colloidal mask made of nanospheres, decomposition of desired materials through the mask. The mask which is removed and the layer keeps the ordered pattern of the mask interstitched. So that is what we are having a lithography. In the same way, we have seen about the bottom-up approaches. So in bottom-up approach, we are having two types. One is by vapor phase formation and another one is by liquid phase formation here. So vapor phase formation, in which the precursor is nothing but the starting material for the manufacture or the synthesis of the nanomaterials here. So the precursor, it may be the metals, or it may be any other gel, or it may be the solid material, or it may be the liquid material which we are going to use. That we call it as a precursor. So by the precursor, by the evaporation, or by the condensation, or by the coagulation methods, we are going to synthesize the nanoparticles. So in the vapor phase formation, by the evaporation, gas phase reaction, gas to solid surface reaction. So here we come across supersaturation or nucleation and condensation, as well as agglomeration, grain growth, nucleation, grain growth, which leads to the synthesis of the nanomaterials. That is what we are having in the vapor phase. That is the material which converts to the vapor, and that vapor by the which is converted to the solid state by using by the condensation, or it may be the nucleation, or it may be the grain growth. Like this, we get by the agglomeration, we get the nanoparticles. In the liquid phase formation, the precursor which is in liquid phase reaction, by the liquid phase reaction, liquid solid surface we get. So here also we come across the liquid solid surface reactions. We come across the nucleation or condensation, agglomeration and grain growth, which leads to synthesis of the nanoparticles. So that is what we are having, the different type of the approach here. So today we will discuss about the one of the method, what we call it as the wet chemical synthesis or sol-gel method. We call it as a sol-gel method. So before going to this process, we'll see why we call this process as wet chemical synthesis. Why we call it as a wet chemical synthesis? Because the name itself indicates wet chemical. That is, here the chemical substances which we are going to use will be in the wet state. The condition will be in the wet state. So because of this, we call this as a wet chemical synthesis. So it is an bottom-up approach. The sol gel method or the wet chemical method, which is an bottom-up approach. By the atomic level, we are going to convert to the nano level here. So next we will see why this process is called as sol gel method. So here it is in a wet condition, wet chemical synthesis it is, where the moisture content will be there. In this process, the moisture will be contained. So we call this as a wet chemical. And sol gel, why we call it as a sol gel is, in the synthesis of the nanoparticle, we come across the one stage called as sol. And the another stage we call it as we get a gel. So sol is nothing but the colloidal suspension. The colloidal suspension which we are going to get, and this sol will be converted to the gel, that is the gel formation here. So in this process the nano-sized metal oxides formation takes place here. So then what is a precursor here? We get the end product, that is a nano-sized metal oxide. But what is a precursor? That is what is a starting material for this synthesis of the nanoparticles. So here in this process we are going to have a precursor as metal alkoxide. The metal alkoxide, which is the starting material for the preparation of the nano material here. So you can see here the sol gel process is a wet chemical technique. Already I have discussed this, known as a chemical solution deposition, widely used recently in the field of material science and ceramic engineering. So material science, in the field of material science and ceramic engineering, this sol gel technique plays a very important role here. So this is the process what we are having, that is the formation of the stable gel, gelation via a poly-condensation or polyesterification reaction, gel aging in a solid mass. This causes contraction of the gel network, also phase transformation and oswald ripening here. So drying the gel to remove the liquid phase. This can lead to the fundamental changes in the structure of the gel. Dehydration at temperature as high as 8000 degrees Celsius used to remove the group MOH. That is nothing but the what we call it as a gel which we are having, that is the metal that is the sol group MOH, which is a sol group which is removed from the gel, the group of stabilizing the gel, that is to protect it from rehydration. Densification and decomposition of the gels at high temperature, that is more than 8000 degrees Celsius, to collapse the pores in the gel network and to dry out remaining organic contaminants. So this sol gel technique, the evolution of inorganic network through the formation of colloidal suspension, that is the sol, and gelation of the sol to form a network in a continuous liquid phase, that is the gel. So here in this process, that is the metal alkoxide, which is converted to the metal oxide by the transformation of metal alkoxide to the sol, that is the colloidal suspension, and that colloidal suspension, that is the sol, which will be reacted with the metal alkoxide to form the gel here. So that gel, whatever the gel we get, from that gel we are going to get the nanoparticles here. So with the gel, which is a continuous liquid phase, what we are having, from this continuous liquid phase we are going to extract the nanoparticles. So we are going to have another process here for the extraction of the nanoparticle from the liquid phase, continuous liquid phase, that is the gel. So this is the process what we are having in the sol gel technique here, that is mix the reactives. That is here mixing of the reactive is nothing but here the metal alkoxide, which is metal alkoxide. For the metal alkoxide we are going to add the water here. So to dissolve the metal oxide, we use the catalyst as in water here. But what happens here is the water, by using water, we cannot dissolve the metal alkoxide here. So that is what we are having. So in water, the metal alkoxide will not dissolve. So because of this, before going to add the water, the alcohol in small quantity, that is in terms of the solute, we are going to add small quantity of alcohol to the metal alkoxide, so that the dissolve of the metal alkoxide takes place, and then we add the water here, so that the continuous dissolve which takes place, and water acts as a catalyst here. So after adding the metal alkoxide, then the alcohol, small quantity of alcohol and water, then we go for continuous stirring, which leads to the formation of the hydrolysis, which takes the hydrolysis again. Then it gets the hydrolysis, and condensation reaction takes place here. So the precursor, that is metal alkoxide plus alcohol plus water, which is a homogeneous solution here. So this is a homogeneous solution where the metal alkoxide which react with the water to get the hydrolysis, reaction here. So when the hydrolysis reaction which takes place, here water acts as a catalyst, so that the hydrolysis reaction takes place. When the hydrolysis reaction takes place, we get the sol material here. So we are going to see the sol here. So the sol which is a metal hydroxide. Sol is nothing but the metal hydroxide it is. So metal hydroxide which will not soluble in water. So here the metal hydroxide, what we get, this metal hydroxide will not solve or dissolve. It is not insoluble. It is not soluble in water. So we call this as a colloidal suspension. Why we call sol as a colloidal suspension is because it will not soluble in water. So metal hydroxide will not dissolve in the water. So because of this, we call it as a we call this as a colloidal suspension. So here the sol which we get, it is an heterogeneous solution it is. So it is an heterogeneous solution where it is having that more than one phase here. So that we call it is which is in the form of an heterogeneous solution. So to get the gel, that is jellification. Jellification is a process. Jellification is nothing but the sol which is kept undisturbed. The sol what we get, that is a metal hydroxide solution, that is a colloidal suspension what we get. If we keep this colloidal suspension for some time, if we keep this sol material for undisturbed, if we keep it for undisturbed, that is keeping for aging, that is if we keep it for an aging, so that the sol which converts to the gel, the sol which, that is the jellification, after that we get the gel, that is an what we get, it is an heterogeneous solution. The gel what we get, which is an heterogeneous the condition what we get. And if we keep this gel that is the sol which is converted to the gel, and the water molecules will evaporate here. So water molecules which will be evaporated, and after evaporation it is sent to the condensation process, that is condensed each other, that is condensation reaction takes place. The gel which is an homogeneous, again the gel which will be converted to the homogeneous state here. So the gel which will be in the form of an homogeneous, that is homogeneous, where it is having a metal oxygen bond formation takes place. Metal oxygen bond formation takes place. That is metal oxygen might let metal oxide bond takes place by the polymerization reaction. By the polymerization reaction, metal oxygen bond formation takes place here, so that the nanomaterial is formed here. So if we get this metal oxide by the polymerization technique, then the nanomaterial formation takes place. But here, if we get the nanomaterials, but it will be with the gel here, which will be in the term of the gel here, that is in form of the liquid state it is. So to convert that, is to synthesis or to extract that nanomaterial, we have to go for the extraction method here. So in the extraction method, so at this stage we get the nano-sized metal oxide, but we are going to have, with respect to metal oxide, we are going to have the alcohol content, because to dissolve that metal alkoxide we have added small quantity of alcohol here. So the metal oxide, what we get right now, it is a combination of metal oxide and alcohol here, so that it will be in terms of the liquid state we are having. So that is, we have to get that is drying the gel. Here we get the gel, which is the combination of the metal oxide and the alcohol. So in the extraction process, the alcohol has to be extracted or eliminated from the nanomaterial, so that we get the nanomaterial individually here. So for the drying this gel, the drying of this gel, that is after the gel formation, we are going to have a drying process. Drying is nothing but the extraction of the nanomaterial from the gel here. So extraction of these nanoparticles are in of 3 stages. So that is the first stage, that is of 3 types. In the first type, the gel which is heated under supercritical condition. The gel formation, what we get, the gel formation, if we go for heating under supercritical condition, so supercritical is nothing but the heating the gel above its critical temperature, so that the gel which is in the form of a compound is subjected to the temperature and pressure above critical point, heating above the critical point. And when we heat above the critical temperature, we get aerogel material. So aerogel material, it is an nano-sized metal oxide. But here the morphology, when we go for heating the above its critical temperature, we are going to get aerogel material. But this aerogel material, which is having the morphology, that is, it retains its morphology. That is nothing but retention is nothing but it retains its shape and size, where it is an highly pure state we get here. That is the material what we get right now, the nanomaterial, which will be of highly impure in nature. But this technique, the supercritical condition extraction of nanoparticle, this is an economical, which will be having high economy. It costs high economy. So because of this technique will be adopted. It is adopted whenever it is necessary. That is, it is not frequently utilized. The process, that is supercritical condition, is not applied frequently, because it is not an economic one, and to attain this at a high supercritical temperature, to maintain the gel at a supercritical temperature is not an easier task here. So because of that, this the technique supercritical heating is done only in a frequent times, that is whenever it is necessary. So by the another technique is by thermal evaporation. So thermal evaporation is nothing but here heating the material above its room temperature. That is, heating and evaporating, which leads to the formation of zero cell material. In the zero cell material, morphology changes here, so it does not retain its shape and size, so that it is an economic one what we are having, so that we can synthesize the, or we can extract the nanoparticles. And another last method of extraction of the nanoparticle from the gel is by calcination process. This process is frequently adopted one in when we are going to synthesize the nanoparticles from the metal alkoxide. We frequently use the technique is the calcination technique here. So calcination is nothing but heating in the presence of oxygen at high temperature around 600 to 800 degrees Celsius. So calcination is nothing but heating the gel material under the oxygen, in the presence of oxygen, at around 600 to 800 degrees Celsius. At that time we can extract the nanomaterial here. So right now we got the nanomaterial. The nanomaterial is nothing but the metal oxide here. So in this process, this is the process what we are having. So I will I'll explain once again how exactly the sol gel techniques takes place. First we have to add the precursor. Precursor is nothing but here, precursor which is nothing but the metal alkoxide which is added with the water. When we add the water, it does not dissolve. Metal alkoxide will not dissolve with water. So before adding the water, here water acts as catalyst. So before adding the water, we have to add a small quantity of alcohol. So metal oxide with alcohol we have to add, and we have to dissolve the metal oxide with the alcohol here. By the stirring, continuous stirring, we have to dissolve. When it dissolves, we have to add the catalyst, that is the water. When we add the water to the metal alkoxide plus alcohol, the hydrolysis reaction takes place. So right now it is an homogeneous solution what we are having. So metal alkoxide, alcohol and the water, right now it is an homogeneous solution here. So when we add the water, the hydrolysis reaction takes place. When the hydrolysis reaction takes place, the sol material will be, we are going to get the sol material. Sol is nothing but the metal hydroxide. So when the hydrolysis reaction takes place, we get the metal hydroxide. So metal hydroxide which is not soluble in water. So this metal hydroxide what we get, it does not dissolve with the water, it does not soluble in water. So because of this, we call this as an colloidal suspension. Sol is an colloidal suspension which is an heterogeneous in nature, heterogeneous solution it is. So this salt which will be kept for undisturbed for some time. So when we keep it for some time, due to the aging, the salt will convert to the gel. So the gel what we get, it will be of a homogeneous condition. It will be in a homogeneous. So gel is nothing but here metal oxygen bond formation takes place by the polymerization here. So metal oxygen bond formation takes place by the polymerization process. So that we get the nanomaterial is formed here. So the gel material what we get, it contains the nanomaterial here, but we have to extract the nanomaterial from this gel. So when we have to extract the nanomaterial with the gel, because here metal oxide which contains the alcohol here, because we have added the alcohol, so metal oxide which contains the alcohol, so that it does become the gel here. So right now we have to eliminate the alcohol content, then we have to extract. By this we can extract the nanoparticles here. So the gel has to dry here. So drying is done. The drying is done by the three techniques, that is by the supercritical condition, the thermal evaporation and calcination. So most of the cases we prefer the calcination technique here. So calcin, that is extraction of the nanomaterial from the gel here, so that the alcohol content will be eliminated. So to eliminate this alcohol content, and to extract the nanoparticle we prefer the calcination technique. Calcination is nothing but the process of heating the gel in the presence of the oxygen here at high temperature of around 600 to 800 degrees Celsius. When we go for heating, we get the nanomaterial here. Nanomaterial is taken place. That is, nanomaterial is nothing but the metal oxide. Nanomaterial is nothing but the metal oxide. So elimination of alcohol takes place so that we can extract the nanomaterial from the calcination technique here. So this is the process of the sol-gel method or wet chemical synthesis of nanomaterials. So in this we come across some of the reactions. So we have seen jellification, aging, soaking. These all are the process which I have undergone. So here in this I have told you the metal alkoxides are used. That is tetramethoxysilane and tetraethoxysilane. These as well as metal chlorides. These all are the precursors which we are going to use, and these are reacted with water. So the three process which takes place here, that is the hydrolysis, poly-condensation, poly-condensation process which takes place. So here we are going to have the reaction, that is hydrolysis. When the hydrolysis takes place, that is MOR, which is nothing but the metal alkoxide. MOR is nothing but the metal alkoxide which is reacted with water. H2O is nothing but the water. When it is reacted with water, we get metal hydroxide, MOH. MOH is nothing but the metal hydroxide. Metal hydroxide is nothing but the sol what we get. The sol what we get, that is nothing but the colloidal suspension here. That is nothing but the colloidal suspension here. So R is nothing but the alkyl group. R is nothing but the alkyl group, which is nothing but CH3 or C2H5. That is the methane, or it may be terpene, etc. Those are the material. M is the what we are having, the silicon, the aluminum, titanium, etc. These all are the metals which we are going to use. The silicon, aluminum, titanium, these all are the material which we are going to use. That is what we are having. So when we take an example of the silicon, we are going to, by the hydrolysis and reesterification, we get the silicon hydroxide. So silicon hydroxide, in this example, we have taken silicon with the the alkoxide with the water. When hydrolysis takes place, we get the silicon hydroxide what we are having. That is the first reaction which takes place here. So the material, that is the silicon hydroxide, which is nothing but the sol, that is the colloidal suspension what we will get. Next is the poly-condensation process. So in the poly-condensation, that is the colloidal suspension what we have got, that is the metal hydroxide. It does not dissolve with water. Here. So the metal alkoxide, again it is reacted, the metal hydroxide, that is OR, that is the alkyl group, with the MOH, that is the metal hydroxide, which is reacted with the metal, which is reacted with the metal alkoxide, to get the gel here. To get the gel, that is gel is nothing but MOM. The MOM what we have got here, MOM is nothing but that is metal oxygen bonding, metal oxygen, that is the metal oxygen formation takes place by the polymerization process. We get the metal oxygen bond formation which takes place. So this MOM is nothing but the gel formation. Takes place. From the gel, we are going to extract by the calcination technique. The gel which contains metal or oxygen content with the alcohol here. So the alcohol has to be eliminated because of the content of alcohol we are having in the terms of the gel here. So to extract nanoparticles, we have to go for calcination technique. Calcination is a process where heating the gel with the oxygen at around 600 to 800 degrees Celsius, where we are going to extract the nanoparticles here. So by the calcination process, we can extract the nanomaterials. We get the end product as metal oxide, which is nothing but the metal oxide, which is nothing but the nanomaterial here. So in the example, they have taken silicon hydroxide, which is with the water condensation hydrolysis. The first reaction what we are going to see, it is nothing but the silicon oxygen, silicon oxygen, silicon oxygen. That is the metal oxygen bond formation which takes place. So this will not dissolve with water. So it does not dissolve with water. Because of this, again we are going to have a silicon hydroxide. With the silicon hydroxide, with the silicon alkoxide, we are going to have the reaction by the alcohol condensation, that is removal of the alcohol here. So if we remove the alcohol from the gel, the gel formation takes place in the first reaction. The gel which is reacted again with the metal alkoxide, where we are going to have a silicon oxide or silicon oxygen bond formation which takes place, where we have to eliminate the alcohol in this, so that if we extract or if we go for a condensation process, alcohol condensation, which results in the formation of the metal oxide, that is silicon oxide formation takes place here in this, so that we get the metal oxide, which is nothing but the nanomaterial. Silicon oxide is nothing but the nanomaterial which has been extracted here. The end product is the metal oxide, that is nothing but the nanomaterial here. So these all are the reaction with respect to that. These all are the reactions, that is the how exactly the salt formation takes place, how exactly the gel formation takes place. So you can see here. So the first reaction, which is the hydrolysis reaction, the gel formation takes place by the poly-condensation, followed by the poly-condensation again. So by the reaction with the water, again we get, that is the hydrolysis with we get the MOM. Again we go for reaction with the MOR plus MOH, which we get the MOM. So that is what we are having. The gel formation takes place by the aging, the continuous aging. By the continuous aging, we can go for the removal of the alcohol. Drying, where drying is nothing but keeping it, extracting the material. So aerogel, the aerogel formation takes place when we go with the supercritical heating. By the supercritical heating, we get the pure material, that is nothing but the aerogels. Aerogel, the silicon oxide, low density aerogel. So this is an aerogel material. When we go with the supercritical temperature, when we heat it under critical temperature, supercritical condition, we get the aerogel, which is in pure form. It is in a pure form we get here. So that is what we are having. So zero-gel, that is the silica alcohol. By the evaporation, we get silica zero-gel. So when we go with respect to the thermal evaporation, when we go with the thermal evaporation, heating and cooling process, when it takes place here, that is evaporation. By the evaporating, we get the zero-gel, which is nothing but here the morphology goes on changing. That is, you can see here the first figure what you are having, and the second figure what you are, that is the silica alcohol we are having, but we get the silica zero-gel. So here we are going to see that the shape and size goes on changing here, that is morphology has been changed here. So by the thermal evaporation, shrinkage of pores occurs and the zero-gel formation takes place. Zero-gel formation takes place by the calcination. Next process is the calcination. So calcination, where we are going to heat with oxygen here, that is during calcination, zero-gel is heated up to 800 degrees Celsius. The pores of the gel networks are collapsed and remaining organic species are volatilized. The surface bond MOH, metal hydroxide groups are removed, thereby stabilizing the gel against rehydration. Calcination results in the densification and decomposition of the gel here. So the decomposition of the gel takes place, so that the nanomaterial formation takes place. Extraction of the nanomaterial takes place by the calcination technique. So heat treatment, by heat treatment the material is shaped into desired form such as film, fibers, nano-sized powder. So when we go for heating again, we can make in terms of the film or in terms of the fibers or in terms of the nano-sized part. Subsequently it can be converted into ceramic material. So you can see here, so when we got in terms of fiber, when we are having a fiber, we are going to see the first figure which indicates the fibers, the next figure which indicates the nanoparticle, that is the what we are having here. So this is the nanoparticle powder what we are going to see. So what are the advantages of this sol gel technique? When we go with respect to the advantages, that is cheap and low temperature operation, we are going to have very thin of metals, that is oxides can be obtained, thin oxides can be obtained, better alternative approach to conventional production of glasses. So sol gel material can be obtained as a bulk, thin films or nano powders, all we can go for. So mono-sized nanoparticles are produced by this method, useful for synthesis of glass ceramics or ceramic material at lower temperature. So at lower temperature we can go for extraction of nanoparticles. But the main disadvantages of this is controlling the growth of the particle. So controlling the growth of the particles is very difficult here. Avoiding the agglomeration of newly formed particles, that is what we are having, that is the gel. After gel we have to keep it for aging, and after aging we have to go for extraction. So this process is these processes are very difficult here. So that is what we are having, avoiding the agglomerating of newly formed particles. So these are the disadvantages of the sol gel technique what we have. So application of the sol gel or the metal, the wet chemical synthesis of nanoparticle is protective coatings. Protective coatings can be done. So for the coating purpose we can go for it, because we are going to get a gel, so we can go for a protective coatings, thin film and fibers, nanoscale powders, or optomechanical. We can go for optomechanical also. So optical and mechanical applications we can go by using these nanoparticles, or by the sol gel technique. By this sol gel technique we can go for optomechanical systems or nanoscale powders, thin film and fibers. Protective coatings can be done. Drug delivery system, anti-corrosion barrier coatings, that is the coating what I have explained. UV protection gel, that is ultraviolet protection gels can be made. Lubricants and scratch-free paints. Lubricants and scratch-free paints can be manufactured. New, that is fire retardant materials, that is abrasion resistant material, or the new scratch or the abrasion resistance materials. Superior strength fibers and films. Superior strength fibers and films can be manufactured by using the sol gel technique. So nanoparticles can provide significant improvement in traditional biological imaging of cells and tissue using the fluorescence microscopy, as well as in modern magnetic resonance. These are the future work of nanomaterials. These are the future works. So by these future works can be done in our nanomaterials. So that is what we are having. So this is the technique what we are having in the which is having with respect to the sol gel technique. With respect to sol gel technique, that is nothing but the wet chemical synthesis of nanoparticles. Thank you, students.